We'll now take a look at the translation and loading process. So what must happen in order for the assembly language program to be executed on a processor? Well, before we can actually have a program run, we must invoke two system software packages, and these are called the assembler and the loader. An assembler translates a symbolic assembly language program into machine language. Now, we usually think of translation as an extremely difficult task. In fact, if two languages are different based on vocabulary, grammar, and syntax, and if these differences are very large, then this can be quite a difficult task. And this is why a translator for a high-level programming language is a very complex piece of software. Now, fortunately, for machine language and assembly language, they're very similar. So therefore, the assembler is a relatively simple piece of system software. So it's not that difficult to do this translation. Now, the assembler itself must perform the following four tasks, none of which is really that difficult. It looks like it's difficult, but it's pretty simple to do. So we need to convert the symbolic opcodes to binary. We then need to convert these symbolic addresses to binary. We then need to perform the assembler services that's requested by the pseudo ops. And then finally, we need to put the translated instructions into a file for future use. The conversion of symbolic opcodes, such as load, add, and subtract, to binary values makes use of a structure called the opcode table. This is an alphabetized list of all legal assembly language opcodes and their binary equivalents. So for example, maybe we have an entry for the add instruction and the corresponding binary value would be 0011. To look up the code in the opcode table, we would need to search for that particular opcode. So the assembler will find the operation code in one column of the table and then replace the characters with the corresponding binary value in another column of the table. Now, the way we would do this, you may think, well, we'll just do a sequential search to go through the list, but we could have a very large number of opcodes, so this could really slow down our system. But fortunately, we can take advantage of the fact that our opcode table is going to be sorted alphabetically, which means we can use the more efficient binary search algorithm instead of having to do a sequential search. After the opcode has been converted into binary, the assembler must perform a similar task on the address field. So it must convert the address from a symbolic value into the correct binary address. So for example, we would convert X or loop to a binary address. Now this task is a bit more difficult than converting the opcode because the assembler itself must determine the correct numeric value of all symbols used in the label field. There is no built-in address conversion table equivalent to the opcode table that we just talked about. So in assembly language, a symbol is defined when it appears in the label field of an instruction or data pseudo-op. So specifically, the symbol is given the value of the address of the instruction to which it's attached. Now, the way assemblers will help with this is they'll actually make two passes over the source code. And what we mean by a pass, we're talking about the process of examining and processing every assembly language instruction in the program, one instruction at a time. So during this first pass over the source code, the assembler will look at every instruction. It's going to keep track of the memory address where the instruction will be stored when it's translated and loaded into memory. So we're scanning each line and we're keeping track of the symbols, we're keeping track of the instructions, the memory address is. And it does this by knowing where the program begins in memory and knowing how many memory cells are required to store each machine language instruction or piece of data. It will also determine whether there is a symbol in the label field of that instruction. And if so, it's going to enter the symbol and the address of the instruction into a special table that we're building during this whole process, which is what we call the symbol table. Here is a simple example of some assembly code and then a symbol table, and we can kind of see this process of creating this symbol table. So the idea is we're going to scan through our assembly code, and anytime that we encounter a symbol or a label, we're going to store that label as a symbol and the corresponding address of it into our symbol table. Now, as far as the address is concerned, we're not necessarily storing the exact memory address, but we're storing the address relative to where the program begins. So notice that we have this location counter right here. So this is keeping track of which instruction we have for each line. So each line of code corresponds to a particular instruction line, so that way we kind of know where in our program these symbols exist. So for instance, we have loop here for our first instruction. So we have loop. It's a horrible circle, but we'll go with it anyway. And so what this means is in our symbol table, we're going to store loop, and then the address value is going to be our location counter. So it's going to be 0. And then if we keep scanning down in our assembly program, we'll see that we have the label done. So we have that down here. So that gets stored over to the symbol table. And notice that our location count at this point is going to be 7. So the address value of this is going to be 7. And then we also do this for our data. So we're doing this for any other labels. So we do this for X and Y as well. So those are going to get stored in the symbol table. And we store the address values, which will be the location counter values. So that's going to be 9 and 10. So the idea with this is that we're going to scan the instructions, and whenever a label is associated with an instruction, we're going to add the label memory address pair to the symbol table. So this process of associating a symbolic name with a physical memory address is called binding. And the two primary purposes of the first pass of the assembler are to bind all the symbolic names to address values and to enter those bindings into the symbolic table. So when we add an entry into the table, we're basically adding a binding that exists in our program. So like from our example, when we had our instruction in X, we would add loop 0 to the symbol table. So here, anytime that we find loop in an instruction, we will look up the symbol table to get the label's address. Now for each instruction that we read, we need to know where that instruction is actually located. So we're going to use a variable called a location counter to keep track of the memory address for each instruction. We also use the location counter to track the memory addresses of the discovered labels, and we kind of saw some examples of that where we would add the location counter for every label that we have. So once we read an instruction, so as each instruction is read, we would just increment this counter by 1, just that way we know exactly where we are in our program. During the second pass, the assembler translates the source program into machine language. It has the opcode table to translate mnemonic opcodes to binary, and it has the symbol table to translate symbolic addresses to binary. Therefore, the second pass is actually relatively simple because it involves 2 table lookups and the generation of 2 binary fields. So, for example, let's say we want to translate the instruction subtract X. And we'll assume that our instruction format is a 4-bit opcode followed by a single 12-bit address. So what the assembler is going to do is it's first going to look up the subtract instruction in the opcode table, and it's going to place the 4-bit binary value, which in this case we're going to say is 0101, into the opcode field. The next step would be that the assembler would look up the symbol X in the symbol table, and it's going to place the binary address value. So here we're going to say it's 000000001001, so decimal 9 in this case, into the address field. So after these 2 steps, the assembler will just produce the 16 bits instruction. We're basically combining the opcode binary number and the address binary. So 0101000000001001. So we get this as our final instruction. And this is the correct machine language equivalent of the assembly language statement subtract X. Now, when it's done with one instruction, the assembler is going to move on to the next and then translate it in the same fashion. And this just simply continues until it sees the sudo op.end, which will terminate the translation. The other responsibilities of the second pass are also pretty simple. So it needs to be able to handle data generation pseudo ops. So like in our case, only the .data pseudo-op would be one of these data generation pseudo-ops. So the whole point here is that the .data pseudo-op is going to ask the assembler to build the proper binary representation for the signed decimal integer in the address field. So to do this, the assembler must implement the signed magnitude integer representation algorithms that we have already described. Another thing that the second pass needs to do is to produce the object file needed by the loader. So the whole point here is after all the fields of an instruction have been translated into binary, the newly built machine language instruction and the address of where it is to be loaded are written out to a file, which we call the object file. After completion of both passes, the object file contains the translated machine language object program. Now, this object program then becomes the input to yet another piece of system software, which we call the loader. And it's the task of the loader to read the instructions from the object file and store them into memory for execution. Now, the way it's going to do this is it's going to read the contents of this file. It's going to read the address value, it's going to read the machine language instructions, and then store those instructions into the specified memory addresses. So the idea is it sees the memory address in the file, it's going to go to that address in memory, and then it's going to store the instruction that's associated with that address in the object file. And this operation is simply repeated for every instruction in the object file. Now, when loading is complete, the loader places the address of the first instruction, so like in our example, it would be 0. It would place this address in the program counter to initiate execution. And then the hardware, as we've already talked about, would then begin to fetch, decode, and execute the instructions, starting with the first instruction, whose address is located in the program counter. So we get to the beginning of the program. The program counter has the first address of the beginning of our program, so it's just going to fetch that instruction, it's going to decode and then execute it, and we're just going to repeat this cycle until the program is complete.